Okay, it is my pleasure to introduce our last speaker and my friend, Khadim War from IMPA, Brazil, and he will speak about Margulis estimates for geodesic flow on homogeneous surface without conjugate points.
Okay, thank you, Luciana. Thank you, the organizer, for the opportunity to speak here. I'm sorry for the previous speakers. I arrived here today at 5 in the morning, so I needed to have a nap to be able to make it to my talk. Hopefully, I will say something meaningful. Okay, so we will talk about Margulis estimates for the geodesic flow on homogeneous surfaces without conjugate points. So this is a 45-minute talk. So there are things that I will not define properly, but if someone interrupts me, I will say the exact definition. Like to be able to do maybe all I want to do, I will not define something that are very, maybe standard to some people. But if you tell me, oh, I'm not familiar with this, I will stop and define it correctly, okay? So we start by let MG be a smooth surface, a closed surface. And we denote this by the Gauss curvature. The Gauss curvature is denoted by K. So G is a metric. So for a geodesic C, if let C from R to M be a geodesic. Now we say that for T1, just to define what it means to of conjugate points, I'm sure most of you know it, but for T1, T2 in R, we say that, oh no, before that, sorry. I'm sorry. I should, okay, I'm sorry. So we are given a geodesic. I want to define first what the Jacobi fields mean, and from there I can define what conjugate points are. So G from R to TCM. By TCM, I just mean the tangent space along the geodesic. TCM is a Jacobi field. If it satisfies the following first order plus K CT JT equals 0. So Jacobi fields is just a simple solution of this second order differential equation. Now we say that for T1, T2 in R, we say that CT1 and CT2 are conjugate if there exists J from R to TCM, Jacobi fields such that the Jacobi field that vanishes at these 2 points, J of T1 equals J of T2 equals 0, and J prime at T1 is different from 0. Like you have a non-vanishing Jacobi field, not constant Jacobi fields. Like let's say this is your geodesic C. Let's say this is CT1, this is CT2. The picture you would have would be something like this. You have a Jacobi fields along this geodesic that start being 0 here and be 0 here again. So this is the definition of 2 points are conjugate. And so we say that M doesn't have conjugate points if there is no geodesics which have conjugate points. Sorry? I don't understand.
J prime of T2, you say?
Yeah. It can be 0. You just start at the start. You just want it to grow at the start, yes. Yes.
So for those of us who are not reading the script, can you say what is it?
So
What is the
basically, the geometric, so I don't want to write that, but I will just say it. The intuition behind conjugate points is that you don't have minimality of these geodesics. Like if you are in the sphere, you have two geodesics that are doing like this. If you have this picture that you have 2 points, P and Q, that you can join by two ways, like you don't have minimality of geodesy, you can construct a Jacobi field that is vanishing here and there. But actually, there is this remark. Let me see it now. So M has no conjugate points. Conjugate points. This implies that geodesics are minimal in the universal cover. In the universal cover, in M tilde. You can basically see this by just knowing how to construct. You can construct Jacobi fields by just taking geodesic variation. And if you take a geodesic variation, you will see that the Jacobi fields will be given by exponential of the vector that you started with, like the exponential map. And that being a diffeomorphism would imply that you have minimality of these geodesics on the universal cover. Yeah. So first of all, it's easy to see that in non-positive curvature imply no conjugate points. And yeah, and also there is this well-known result first by Hoff in the two-dimension torus without conjugate points are flat. Like if you consider you have a torus without conjugate points, you can really prove that the Gauss curvature is zero, like the metric is flat. So that's why I'm interested on higher junior surfaces here, because I don't want to consider flat metrics, because the geodesic flow I want to consider, I want it to have positive topological entropy. So I'm ruling out this case. So this is why I have that. And now, yeah, now I can basically state what I want to prove today. So given T positive, you let PT be this number, the number of free homotopy classes containing periodic orbit of period less than T. So yeah. So PT is a number of free homotopy classes that contains a periodic orbits, a closed geodesics. Okay, I should have said closed geodesics. Yeah, closed geodesic. Yeah. So basically, the theorem is about estimating this number, which is called Margulis estimate. So that I will discuss today. This is a joint work with von Climenhaga, Gerhard Knieper, who is in Bochum, and myself. So basically, we say that if let M G be a closed surface of genus, be a closed surface without conjugate points, of genus greater or equal to 2. So I'm doing this just to, because in this case, you can know that your geodesic flow has a positive topological entropy. I can maybe say why later. Then you have this limit when t goes to infinity of pt over eht over t over ht equals 1. Where h is the topological entropy for the geodesic flow. Where h is the topological entropy of the geodesic flow. Yeah, so this is about having an exact asymptotic rate of the growth of these homotopy classes that contains a periodic orbit. Yes. So there is this remark that I want to say in the negative curvature case. Every free homotopy class contains at most one closed geodesic. So this is a key problem that we face when you try to generalize things from negative curvature to non-positive or to no conjugate points. This is just because in negative curvature, we know that the geodesic flow is Anosov. So it is expansive. So you cannot have two orbits that stay bounded at a bounded distance for all time. So which is this, but in the non-conjugate, even in the non-positive curvature case, you can think of these flat strips. You might have, like you can think of this picture here, where all these geodesics, they belong to the same free homotopy class. They are, yeah.
Can I ask a kind of naive but difficult question?
Okay. I'm afraid now.
Can you explain why we should be interested in this?
I don't know the answer. Yeah.
But this has some implications.
Well, already, if you have this, one first implication would be that you have the growth is like the entropy that gives, for instance, a way to approximate the measure of maximum entropy just by averaging along closed orbits. That's one way you do. By knowing the rate of growth of periodic orbits is like the entropy. If you take like a distribution along periodic orbits, at the limit you get a measure of maximum entropy. That's one thing. Yeah. Mm-hmm. Yeah. That's what I can think of now.
For the existence of the measure
No. This uses the uniqueness. This uses the property of the measure of maximum entropy being unique, ergodic, and stuff. We will see that later. So just to say that in negative curvature, this was done by Margulis. And and very recently, for cut zero spaces by Russell Riggs. He was a student of Ralph Spatzier. And actually, in this setting that I'm considering, there was in our setting, Gerhard Knieper and Michel Cornell and Gerhard Knieper. They have proved that you have this bound, Pt is less than exponential of Ht, which is greater than exponential of Ht over T. over HT, sorry. Yeah, so mainly our results push this to have a better bound here, like an exact asymptotic bound. And I will say, I will write a lemma that would give a little bit of the flavor of the proof of this kernel, so which I will need later. This lemma that for every gamma, oops. Oh. So, yes, for every t, yes, yes. I mean, it should start with t large enough. Yeah, yeah. For t large enough, this is the bound you get, yes. So, let's denote by gamma as the group of isometries of the universal cover. I mean, it's standard that the fundamental group is isomorphic to gamma, like the elements of the fundamental group that acts like isometries on the universal cover, and M tilde is a compact quotient by this group of isometries, and there is this lemma that for all gamma in gamma minus the identity. At what time did I start? At what time did I start? At 4, okay. So now it's 25 minutes or, okay, okay, okay. So there exists a C from R, oops, I'm sorry, I've been very, so L, there exists Q0 such that distance between Q0, gamma Q0 is exactly the infimum of distance between Q and gamma Q, where Q is in M tilde. Like there is a point that realizes infimum, and moreover, if C from R to M tilde is a geodesic joining Q0 to gamma of Q0, then you have this property that C is left invariant by gamma, like gamma of CT equals CT plus this quantity. And C projects to a closed orbit, to a closed geodesic. Projects to a closed geodesic. This is very, very general. It uses just the fact that you have no conjugate points. If you don't have, if you consider manifold without conjugate points, there is this. It is in some textbook the proof, so I will not discuss it. So basically, what is this saying? That you can have a correspondence between closed orbits downstairs and elements of the fundamental group, and this quantity is something that is related to the period of the closed geodesic. This quantity is a multiple of the periods. I should say that. Let's say, and d q0 gamma q0 is an integer multiple of the closed geodesic, of the period, of the length of the closed geodesic. So from this lemma, what they observe, like Körner and Knieper, that counting closed orbit, it boils down to counting the elements of gamma with fixed, because this depends on gamma. You can define it as the size of gamma. So to count the closed orbit, you can count the elements of the fundamental group with size less than t, with size equal t. And what is interesting here is that in the case of surfaces, in homogeneous, we know that there is a background metric of negative curvature. And the fundamental group, it doesn't depend on the metric. It's the same for the metric of negative curvature, and it's the same also for the no conjugate points metric that you consider. So they use the fact that you have such an estimate for these elements in negative curvature and translate it to the no conjugate points metric. So they use that correspondence here heavily. So they prove they do it in general manifold, like they just need to assume that you have a background metric of negative curvature and that you have divergence property. That's another technical property. Maybe I will talk about it later, I don't know. So yeah, so they do it in a more general setting. They call it hyperbolic type manifolds. Now, yeah, now to start about ideas of the proof of the theorem I stated here, I want to construct in a specific way the measure of maximal entropy of the system and show you how to use this construction to prove this estimate. So construction of, so MME is measure of maximal entropy by Patterson Sullivan measures. So I will show you how to construct this by Patterson Sullivan measures. So it goes like this. You consider this quantity, which is called the Poincare series. Like if you take PQ in M tilde and S in R, you have this quantity P of S P Q equals exponential of minus S, distance between P and gamma Q. This is called the Poincare series. And what is amazing here is that this, you have it converging for, like, it's proved by Corner that for S bigger than H, then this is finite. It's finite, and it is infinite for S less than H. And for S less than H. Now, what do we do with this Poincare series? We want now to introduce a family of measures using this. So you define for S bigger than H, and you have a point on the universal cover and P also in there. You define nu P XS as this measure. You take this weight here, PSXX, the sum, Dirac deltas like Stefano was doing this morning along orbits. And here the action is given by gamma. D P gamma X, Dirac delta at gamma X. So here by simple triangle inequality, you can see that this measure is finite by simple triangle inequality. You have implies that nu P XS of the closure. So this is one of the things that I said I won't discuss, but if somebody wants to, it's finite. Like, so I have the universal cover. In the case of no conjugate point, the universal cover is just like R2, and there's a natural way to compactify it so that the boundary is like a circle. So yeah, I did not define it, but you just do it naturally by taking geodesic ray that stay at a bounded distance, you take those, the equivalence classes, you take that to be your boundary, and you can put a topology on it that is compatible with the topology on M tilde. So for now, that's what I will say about this, but if there are questions, I might go deeper. So what happened is now you take Sk going to H, and you consider this limit, nu P, like a weak limit, equals limit when K goes to infinity of ni P x Sk. You might wonder because here I have with this measure, it is acting on this unbounded space. But what is true here is that you can see that this measure is gamma equivariant. Like you have nu gamma p xs at gamma a equals nu p x s a. Like the measure is gamma equivariant. And so you can just do it you can just take the limit in a compact domain, and you use the compact quotient to have the same subsequence limit in the whole space by using gamma equivariance. Because you can use the fundamental group, the group of deck transformation, isometry, whatever you call it, and to have the same sequence everywhere. Now from here, another thing you get is, so by this, you will have also this guy is gamma equivariant. The first properties of this family, this is called the Patterson Sullivan families. P is gamma equivariant. Gamma equivariant is just this property. And you can also prove, maybe I will not discuss the proof, but you can also prove that d nu p over d nu q at psi equals exponential of minus h bp q psi. I will tell you what this is for psi in the boundary. So I told you there is a natural way to compactify it, and the boundary is like a circle. So this quantity here is what? It is a Boltzmann function attached at psi. It is this quantity. Like you can define bpq psi equals the limit when t goes to infinity of the distance between cp psi t q minus t. So this is just the geodesic joining p to psi. Like this is the compactification of the universal cover, and I have here a point psi, I have here p. There is a geodesic joining p to psi, and this quantity is called the Boltzmann function, and if you're familiar with it, the level set of this Boltzmann function, they generate the horospheres. Like you have the zero level set, like for sure, if you put here p, you get 0. So this is a horosphere at psi p. And if q is somewhere here, this quantity is just the amount you move from this horosphere to cover p, because this horosphere, they give a foliation of this compactification. You'll have this property. So there is a time. All these are, you have flow going like this to reach the other horosphere. So this time is the same for all of them. So that is exactly this quantity here. And another important property is that, okay. Another important property is that these measures, they are fully supported in the ideal boundary of, actually, I did not say why these measures, they are supported in the boundary, because here, if you look very well, you have this quantity that is going to infinite, because this diverges when S equals the topological entropy. And this is a discrete subgroup, so the support of this measure, of the limit of the measure, will be in the boundary. I did not say that. And actually, another important property is the support of nu p is the whole boundary, is fully supported in the boundary. This is very important. To see it is not very difficult, because what you have, if psi is not in the support of nu p, then gamma psi is also not in the support. This you have it by gamma equivariance. So, for instance, if you have mu which is not in the support, which is not in the mu in the boundary, not in the support, not in the support of nu p, you can have that gamma nu like is not in support. And for instance, so there is something, another property of this geodesic flow that gamma acts minimally on the boundary. This is a result that is proved by Eberlein that in this case of geodesic flow on surfaces without conjugate points, you have that you have topologically transitivity. There is a dense orbit, so gamma acts on minimally. So what you will have is that the support is empty, and this will be in contradiction with this, the measure is not, they are absolutely continuous with respect to each other. So this is a way to prove this. So now from these measures on the boundary, we project a measure now on the unit tangent bundle like this. So let me just define this function. There is this function beta p, which is just a notation minus the diagonal to R that is defined by BP psi eta equals minus BP Q psi plus BP Q eta, where here Q is just a point, Q is a point, can be any in the geodesic joining psi to eta. Let me tell you what this is in this picture. So this is what you have. You have your boundary here, you have psi here, you have eta here, you have this geodesic. Let's say you have a point P here. You draw the holosphere passing through P, and also the holosphere from here passing through P. The holosphere is just level set of that function, as I told you, and this is exactly this distance. This is exactly B beta P psi eta. And after this, we can define a measure on the product now. So we define mu bar on, so mu bar on the product minus the diagonal by, it is just a product measure, psi eta equals exponential of h psi eta p d mu bar d mu d nu p psi d nu p eta. So we have this product measure, and also this product measure is also invariant on the gamma. And from there, we also define a measure now on the unit tangent bundle of the, so let's first define this projection map, like P is from SM tilde. SM tilde is a unit tangent bundle of M tilde to the product minus the diagonal. Oh my gosh. So I will have this, and yeah, this is just given by CV. I will tell you what this is, and CV minus infinity and CV infinity. So this is just, if you give me any vector on the universal cover, I can draw the geodesics passing through this vector, and the two endpoints of these geodesics are given by this map. So I define mu tilde on SM tilde by mu tilde of A equals tilde minus the diagonal supremum of the lengths. So this is also very technical. CV intersect with A, such that V is in P minus 1 of psi eta. And then, yeah. So what you do, you take these 2 points, you have your set A, you take this, the projection of all the endpoints that intersect this set, and you take the longest geodesic that intersect that set, and yeah, do mu bar of psi eta. And clearly, you can see that, sorry? So here, supremum, because here, as I told you at the beginning, I might have problem of having many geodesics connecting 2 points at the boundary, psi and eta, because of the non-expansivity. I might have 2 geodesics joining this. That's why I need to take the supremum there. So basically, you can see that this quantity here, the measure of any compact set is finite. Why? Because this quantity, the only way for it to blow up is that psi and eta are getting closer. Like if psi and eta are getting closer, you have this quantity is getting bigger, like it's blowing up to infinity. And if you take for A in a compact set, then mu tilde of A is finite. And also it's easy to prove that mu tilde is gamma invariant. Mu tilde is also gamma invariant. Then mu tilde induces invariant measure on SM, on the unit tangent bundle of M. And there is this theorem that we prove in our first joint paper. So Climenhaga, Knieper, and myself, that induces a measure, an invariant measure, let's call it mu, that when you project this to the unit tangent bundle of your manifold, that mu is a unique MME, and the geodesic flow is mixing with respect to it. Is mixing with respect to me. Yep. So mixing is just, I saw it this morning in the slides of Sylvain. It's just you take the measure of the intersection of 2 sets where one is iterated by the dynamics is converging to the product of the measure of the 2 sets. I have 1 minute left, but I think maybe I will take 4 more to make it 5. To describe what I want to say. I'm not sure if I can say it in this one blackboard. So after this, what you do basically is you define the usual Margulis estimate. You define what they call a detector. Like you need to define a set, and you count the closed orbit that intersect these sets. And if you are able to prove that the number of closed orbit is like the measure of the set, then you can play the game in the whole space by using transitivity and so on. So To define that set, we define this set like this. So there is this map H, it's called Hopf map, and it's from S of M tilde to times R. It takes V, it gives you V minus, V plus, and BP, PV, I will say. So V plus and V minus are just the two endpoints at infinity, and this projection is just the foot point of the vector. Now, you define your detector like this set as B delta equals H minus 1 of C V0 minus delta times C V0 delta plus times 0 epsilon. So V0 and epsilon are fixed once for all. V0 and epsilon are fixed. So this is just a neighborhood of the point at infinity. Like you have this is V plus, you take a neighborhood of size delta here, and V minus a neighborhood of size delta, and you have this geodesic, and this will be just a set like this here. This is our detector, and you define this B delta T, because what we want to do is we want to detect the closed orbit that passes through this set. The closed orbit should be defined like this. Gamma is B delta intersect gamma star. So V minus T, I would say this is the geodesic flow, B delta. So if I have a closed orbit, like if this was a closed orbit, so this intersection won't be empty if, so V0 is closed geodesic, imply that B delta gamma, size of gamma is not empty. Size of gamma is what I defined at the beginning by the infimum of the distance of gamma and Q of gamma. Because why is this? The geodesic flow will take this and map it here. And I know gamma is just like leave invariant is geodesic, so it will map it back. So I will know this will be non-empty. So basically, to count this, it boils down to counting this set, gamma delta T, is a set of gamma in gamma, such that B delta gamma is not empty. And this is basically the points where now you need to use your properties like mixing and the measure being a product measure. No, I cannot go further. So basically the mixing is used here because at some point you need to estimate the measure of this set, and this being mixing is the measure of this set is like the measure of this set square, like as t goes to infinity. And also you need the fact that this is a product measure. So basically what we want is the cardinality of gamma delta t is like EHT, like of this order times measure of B delta t, like mu of B delta t. And once you have this, because this fixes the period, this fixes the length of the closed geodesic to be exactly size of gamma. And after you do, there is a Riemann sum that you need to do now to get the actual estimate that when you add all of them, like from t equals 1 to t, you divide here by ht. So I don't think there's time to say more, but basically these were key. So I was insisting on the construction of the measure because it is key to use the fact that the measure is a product measure and the measure is mixing. Also in the proof of mixing here, I should say, we highly use this construction of the measure to prove mixing. We basically follow a proof of Martin Babilo, where she proved that as long as your measure is a product measure and sees enough hyperbolicity, you have mixing. And it uses the continuity of what is called a cross-ratio function. For some people who are familiar with the paper of Carlangelo Livrani on exponential mixing for contact analysis of flow, there is what is called a temporal function, which is just you go by stable, unstable, stable, unstable. You have this gap, and the C2 regularity of that gap was what gives the exponential mixing for the geodesic flow. Here we use similar function, but we just have continuity, and it was enough to prove mixing. I think I will stop here. I'm sorry for extending it too long.